In this unit, we'll be discussing circular motion. And for these slides in particular, we'll really get into the calculations of things. I was thinking we'll do most of the conceptual stuff in class, and then I can help you with the calculations on these types of videos. Hope that works for you. And of course, as always, give me feedback if you need more or whatever you need. So this picture, if you take a look at that, it looks like we've got a ball tethered to a string. And it's spinning around what looks to be a counterclockwise rotation. Something you'll notice is that the centripetal force is pointed towards the center, right? The centripetal force essentially is the tension of the string. And so the centripetal force, that's the force making the ball turn, it's towards the center of the circle. Now, this is kind of a closer look at that same situation. The net force required to keep an object moving in a circle is always directed toward the center of a circle. And later when we talk about gravitation, it's going to be a similar situation, right? If something is orbiting a planet, like maybe our moon or a satellite, for instance, the force due to gravity is very similar to the force due to tension on a string that is spinning around maybe somebody's head or whatever. Now, the acceleration is in the direction of the centripetal force, okay? And that's quite important. And some might think, well, if it's a constant velocity, you know, if the thing is going in a relative constant velocity, if you were to just measure the velocity at one time, if that velocity isn't changing, then you might be tempted to think there is no acceleration. However, you have to remember that velocity is both speed and direction. And since the direction is changing, the velocity is changing. And there is acceleration. And that's why the acceleration is pointed towards the center, right? It keeps turning. Essentially, this thing just keeps turning towards the center, right, as it's going around. And that's why that's the direction of acceleration. Your net force is also towards the center, which makes sense because force equals mass times acceleration. So the force and the acceleration must be in the same direction because those are the two vectors there. And the velocity is always tangent to the circle. If you look at those green velocity arrows, velocity is tangent to the circle and basically in a straight line. And if you remember from the beginning of class on either Monday or Tuesday, you remember that when the ball went around the circle, as soon as the ball was released to do, and it was no longer being pushed towards the center by the walls of the circle, the ball just went in the exact same direction its velocity was going at that moment, right? So if you let go, if the centripetal force disappears at any moment, the object would just go in a straight line, exactly the direction it was going, a straight line in the direction of velocity, which is tangent to the circle. So here's a question. I'd like you to think about the answer on your own for a second. But it says a softball pitcher is throwing a pitch. At the instant shown, the ball is moving in a circular arc at a steady speed. At this instant, and the instant we're talking about is where the picture is, right? I've had students think the instant is the end of the arrow, but no, it's right now, right where the picture is frozen. At this instant, the acceleration is directed up, directed down, directed left, directed right, directed at 0. So come up with an answer for that. So if you look at this picture, it actually doesn't matter it doesn't matter where it's frozen. Acceleration is always directed at the center of the circle. So the acceleration is directed right, like basically right at that picture's heart, right at the center of the circle. That's always where acceleration is directed with circular motion. All right, so from the text or from the reading or from Khan Academy or whatever you did, we know that centripetal acceleration, that's basically the acceleration of circular motion, right? It's the curving acceleration. The centripetal acceleration equals velocity squared divided by the radius. And if we substitute that into Newton's second law, so if centripetal acceleration equals velocity squared, if we take F equals ma and we change the acceleration out for velocity squared over r, well then we get centripetal force is equal to the mass times the velocity squared divided by the radius. So now, since we know the circumference of a circle is 2 pi r, And we know the time for one revolution is called the period with the symbol capital T. So, okay, so we know that distance over time is normal velocity, right? That's like the definition of velocity and straight line velocity. Well, that means circular velocity is 2 pi r divided by the period, which you figured that out when you determined how fast my toy car was going when we did that little thing on Friday. So in circular motion, frequency, and that's like a lowercase f. That's why I'm always drawing force as a capital F, because we have a lowercase f that means frequency. So in circular motion, frequency is the number of rotations made in 1 second. Frequency is the inverse of the period. Guys, this tricks students all the time, right? Just confusing period with frequency. So, write that down and take special note. There will be questions that ask you about period. There will be questions that ask you about frequency. And there will be questions that deliberately try to confuse you if you don't know that there's a difference. It's just the inverse. So it's really not that hard to do. You just have to remember that, the frequency is the inverse of the period. All right, so let's take a look at this question here. A boy sits on a horse on a carousel, right? So he's like, the carousel's going in a circle, right? And he's 5 meters from the center. That's the radius, right? He makes 1 revolution every 8 seconds. Okay, so if it takes 8 seconds to go around once, the time it takes to go around once is the period. So the period is 8 seconds, and it looks like calculate the period and frequency. So I didn't need to even, that radius, I didn't need that. I already have the period, it just gave it to me. And he makes a revolution every 8 seconds, so that is the period. And remember that frequency equals the inverse of the period. So frequency is 1 over 8, which is like 0.125 seconds per, revolutions per second, right? Because that, you got to remember, frequency is how many revolutions it makes every 1 second, and it if it takes 8 seconds to go around once, that makes sense. You're going to have a very small number there. All right. So now I got to calculate the boy's tangential speed. Okay, well, all right. Well, remember, he had. Now I actually need to know things, right? I had my 5 meters equals my radius, right? I had my period. Ooh, well, that's fine. Period is 8 seconds. And my frequency, remember, was 0.125 revolution. I'll just say 1 over seconds, right? Revolutions per second. And then I got to figure out his tangential speed. So I'm going to get my little equation sheet out here, right? And, in fact, actually, let's see. So, okay, remember that velocity equals distance over time, right? So you have to remember that velocity actually equals circumference over time, right? And the circumference of a circle is 2 pi r. I already showed you this over, and the time would be the time it takes to go around 1 time, right? So that'd be tangential speed. That's his velocity essentially, right? Well, tangential speed is a better way to put it. Yeah, that's what VC is. It's your tangential velocity, and it basically just means how fast would you be going if you were going in a straight line, right? Like we did with that car. So I've got everything I need here, right? 2 pi times 5 divided by 8. That's all I have to do. So 2 times pi times 5 divided by 8. So his tangential velocity is like 3.9 meters per second. All right. So now I got, if the boy sits on a horse, on same deal, same exact question, If the boy chose a horse closer to the center, excuse me, what would happen to his tangential speed? Okay, well, think about it. Right? So if you're close to the edge, your radius is 5, right? But if you're somewhere in the middle, your radius is shorter, less than 5. Let's say he sits in the middle. Let's say the radius is 2.5, right? Let's just see what happens, right? So you remember that we said that the tangential velocity, we'll say velocity c, tangential velocity, whatever we want to call that. Let's say it was 2 pi times r divided by the period. Well, the period is going to be the same, right? This is a disk. It's spinning around. Any spot on the disk, like if you have a spot here and a spot here, they're going to spin at the same rate, right? So that's not going to change the period or the time it takes to go around. But if the r is smaller, you're going to end up getting half the velocity. So it's going to your tangential speed is going to be slower, which makes sense, right? Because look, you're covering much less area, right? You're covering a smaller circle in that amount of time. Now, it feels a little, it doesn't always feel slower in there, and that's because you're turning a lot more. So you actually have more acceleration going on in that situation, but you do have less velocity. So he would have less tangential speed, I guess is the answer to that. What is the centripetal acceleration of the boy? Well, we just said, well, let's say, remember that our velocity, remember we said that it was 3.9, right? So we need to remember that, and that was meters per second. And our radius was 5 meters. And we straight up have an equation for this, right? Centripetal acceleration is equal to velocity squared divided by the radius, okay? And so I've got everything I need, right? 3.9 squared divided by 5. So let's see, second answer squared divided by 5. I'm looking at 3 centripetal acceleration equals 3, it's 0.08, so I'm just going to go ahead and say 3. And I know my significant figures are a little all over the board, but it's fine. 3 meters per second squared, right? That's meters per second divided by, yeah. Oh yeah, because the velocity is squared, that's right, that's why. Meters per second. You square meters per second and you get meters squared over seconds squared, but then you divide it by meters and it turns into meters per second. That's what's going on. All right, cool. So in case you're wondering about if the units work out, and they do. All right. So what is the magnitude of the centripetal force acting on the boy? Okay, well, we just said that the centripetal acceleration, let's write down everything we have so far, is 3 meters per second squared, right? We know that the velocity is 3.9 meters per second. We know the radius is 5. We know the period was, is 8. Right, so there's all the things we know. What's the magnitude of the centripetal force acting upon the boy? Now, I gave you this equation, but I don't have it. I have to remember that. This is good practice for me to derive these equations. So I'm going to insert this acceleration into the sum of the forces into Newton's third law here, right? So equals ma. I'm going to take this a and substitute it in for, so this is, right, this is acceleration. I'm going to substitute this in for acceleration then. And that means there's only one force I'm dealing with right now, centripetal force. So that's the only one I'm going to worry about. So I'm going to say sum of the forces is just that force. So the force, or the centripetal force, I could say. So let's say, yeah, the centripetal force is equal to the mass times acceleration, which, remember, is velocity divided by, I guess, just the radius, right? So there it is. And I think I have all those things, right? Oh yeah, he's 45 kilograms. So 45 times the velocity squared, 3.9 squared, divided by the radius, which was 8. 45 times 3.9 squared, divided by the radius, which is 8. I get the force acting upon the boy, the centripetal force acting upon the boy is 85.6 newtons. And here's the thing, everybody, and if you've ever been on a ride, like a carnival ride that goes in a circle, right? And you're going, let's say you're going around in a circle like this, right? Boom, 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 you're going around in a circle, right? The force acting upon you is towards the center, right? But because the force, that actually makes you kind of feel like your body wants to remain. This is your velocity, right? So there's your velocity, and the force is pulling you this way, which is the reason you kind of feel like you want to fly that way. That's not real, right? The feeling that you want to fly that way, that's not a real force. The real force is pulling you this way. What you're feeling is the fact that your body's inertia wants to keep going straight, right? And so it feels like you are being pulled to the outside of that circular ride.